Hi students, welcome to online classes. I am M. Sujatabai, working in KGBV Somendapalli School. Today we are discussing our second chapter, Laws of Motion.
In ninth class.
Sir Isaac Newton was born on 25th December 1642, who was a famous mathematician who was the culminating figure of the scientific revolution of the 17th century. In optics, his discovery of the composition of white light integrated the phenomena of colors into the science of light and laid the foundation for modern physics optics. In missions, his three laws of motion, the basic principles of modern physics, resulted in the formulating of the law of universal gravitation. Students, today we are discussing about the topics Newton's first law of motion, second law of motion and third law of motion. Today the first topic is first law of motion. Children, listen carefully. The first law of motion can be stated as every object will remain at rest or in a state of uniform motion unless compelled to change in its state by the action of a net force. Newton's first law explains what happens to an object when no net force acts on it, or either it remains at rest or moves in a straight line with constant speed, that is uniform motion. The body at rest always tries to stay at the same state of rest. It does not accept any change in its position until some force acts on it. This property is known as static inertia. The body, which is in motion, always tries to move in the same direction until some force acts on it. This property is known as dynamic inertia. So, students, finally, Newton's first law of motion is an object either remains at rest or continues to move at a constant velocity unless acted upon by a force. Students, to get the idea of Newton's first law of motion, see the video.
In our everyday life, we observe that effort is required to put a stationary object into motion or to stop a moving object. Have you ever wondered if a ball kicked on the ground would keep moving forever, or after some time would naturally stop moving? The ball will continue to move unless an object of force stops it. Here comes Newton's first law, which states a body continues to be in its state of rest or of uniform motion unless acted upon by an unbalanced external force. To understand Newton's first law, you need to understand what unbalanced force is. If you have seen a game of tug of war, you would have seen two teams pulling a rope in opposite directions. If the rope doesn't move, the forces applied by the teams are balanced forces as they are of equal magnitude in opposite direction. If one of the team applies greater force, it pulls the other team and the rope towards their side. In this case, the forces are unbalanced as the two forces are of unequal magnitudes in the opposite directions. If one of the team lets go of the rope, the opposite team falls backwards. This tendency to fall backwards despite letting go of the rope is due to inertia. That is, if an object is at rest, it tends to remain at rest, and if it is in motion, it tends to stay in motion. This property of an object is called its inertia. Inertia can be classified into three categories: inertia of rest, inertia of direction, inertia of motion. Certain experiences that we have while traveling in a bus can be explained on the basis of the law of inertia. When a passenger is standing in a stationary bus that suddenly moves, the movement pushes the passenger backward. Why does this happen? This is due to the inertia of rest experienced by the passenger in the upper part of his body. The body is at rest when the bus is at rest. When the bus starts all of a sudden, the lower part of the body is in contact with the vehicle that started moving, whereas the upper part of the body continues to be at rest because of the inertia of rest. Inertia of rest is the tendency of a body to resist any change in its state of rest. What happens when a fast-moving bus negotiates a right-hand curve on the road? The passengers will tilt to the left. Inertia of direction is the tendency of a body to oppose any change in the direction of its motion. With the application of sharp brakes, the bus stops all of a sudden and the passengers tend to fall forward. This is due to inertia of motion experienced by the upper part of the body. When the bus is moving, the whole body of the passenger is in a state of motion. A sudden halt caused by the lower part of the passenger's body that is in contact with the bus comes to rest. However, the upper portion of the body remains in the state of motion due to the inertia of motion causing the passenger to fall forward when the bus stops suddenly. Inertia of motion is a tendency of a body to resist a change in its state of uniform motion. Thus, Newton's first law is also called the law of inertia. Well, now this law should make sense. Do you understand why a ball on the ground after being kicked does not keep moving forever? The ball stops after some time due to the unbalanced external force applied by the ground in the opposite direction. Things to remember. Newton's first law of motion states that a body continues to be in its state of rest or of uniform motion unless acted upon by an unbalanced external force. Two unequal, oppositely exerted forces are called unbalanced forces. Newton's first law is also known as the law of inertia. The tendency of an object to continue its state of rest or of uniform motion in a straight line is called inertia. The three types of inertia are inertia of rest, inertia of motion, and inertia of direction.
Students, our next topic is Newton's second law of motion. Newton's second law of motion explains what happens to an object when non-zero net force acts on it. For example, place a ball on the veranda and push it gently. The ball accelerates from rest. So, children, we can say that force is an action which produces acceleration. A non-zero net force acting on a body disturbs the state of equilibrium. Now, we are going to discuss how acceleration of an object depends on force applied on it and how we measure a force. To know about this, now let us see a small activity basing on second law of motion. Students, now let us do a small activity on the topic larger the net force, greater the acceleration. Children, take some ice cubes and a smooth surface. Gently push a block of ice on a smooth surface and observe how the object speeds up. In other words, how it accelerates. Now, increase the net force and observe some changes in its speed. Is the acceleration increased or decreased? Students, let's do another activity on the topic larger the mass, smaller the acceleration. Firstly, apply a force on an ice block. It undergoes some acceleration. Now, take a block of ice with greater mass. Apply almost the same force on this ice block and observe the acceleration. In the both activity, the object accelerates, but we can observe in the second case, it does not speed up as quickly as before. From the above two activities, we may have noticed some points. For the points are, the larger the net force, the greater the acceleration. If the mass of the body is constant and also larger, the mass lesser the accelerations if a constant net force is applied. Finally, Newton's second law of motion states that the rate of change of momentum of an object is proportional to the net force applied on the object in the direction of net force. To get some more idea of Newton's second law, let us see a small video.
Verification of Newton's second law. Arrange a cart on a table with blockade and a pulley. Tie the cart with a twine. The mass of the cart is 500 grams. The twine on the cart is passing over the pulley to a weight hanger. The hanging weight is 50 grams. As soon as the weight is released, the cart starts moving and is stopped by the blockade. Note the distance moved by the cart and the time taken to travel the distance. Calculate the acceleration of the object. Calculate m2g and m1 plus m2 times a. It is found to be the same. Hence, Newton's second law is verified.
Students, our final topic is Newton's third law of motion. Now, let us know about this. Children, now let us do a small activity. Pulling two spring balances. Let's take two spring balances of equal calibrations. Connect the two spring balances as shown in the figure. Pull the spring balances in opposite directions as shown in the figure. What do you notice from the readings in the spring balance? Are the readings of two spring balances are same? Are we able to make the spring balance show different readings by pulling them simultaneously in opposite direction? Why not? According to third law of motion, when an object exerts a force on other object, the second object also exerts a force on the first object which is equal in magnitude but opposite in directions. The two opposing forces are known as action and reaction pair. Newton's third law explains what happens when one object exerts a force on another object. Children, let's know about action and reaction forces. If two objects interact, the force FBA exerted by the object A on the object B is in equal magnitude and opposite in direction to the force F exerted by the object B on the object A. The negative sign indicates that the reaction forces is acting in a direction opposite to that action force. This states that no single isolated force exists. Newton's first and second law of motion apply to a single body, whereas Newton's third law of motion applies to the two objects. Newton's third law of motion applies to an interaction between the two bodies. Note that the forces in Newton's third law never act on the same body. The action-reaction pair in Newton's third law always represents forces acting on two different bodies simultaneously. Let us see some examples about this. Let us see some examples. When birds fly, they push the air downwards with their wings, and the air pushes back the bird in opposite direction, upward directions. Thus, the force applied by the wings of birds on air and an opposite force applied by the air on wings are equal in magnitude and opposite in direction. Let us see another example. Fishes swim in water. The fishes push the water back and the water pushes the fish with equal force but in opposite direction. The force applied by the water makes the fish to move forward. This helps to fish for swimming. Another example, a rocket accelerates by expelling gas at high velocity. The reaction force of the gas on the rocket accelerates the rocket in a direction opposite to the expelled gas. Finally, to get some idea about Newton's third law, let us see a small video, children. Watch carefully.
Newton's third law of motion. Sir Isaac Newton was a 17th century English physicist who discovered three laws of motion. Newton's third law of motion states that for every action there is an equal and opposite reaction. In other words, if object A exerts a force on object B, then object B also exerts an equal force on object A. Notice that if the forces are exerted on different objects, they will not cancel each other. The third law can be used to explain rocket propulsion and the recoiling of the gun. Here are some daily life situations to illustrate Newton's third law of motion. When we walk on the ground, our foot pushes against the ground backward, that's action force, and the ground in turn exerts a force on the foot, that's reaction force, pushing the foot forward. When a man jumps from a diving board, he pushes the board, which is action force, and the board in turn pushes the man forward in the opposite direction, which is reaction force. Birds, while flying, push the air downwards with the help of their wings, which is action force, and the air in turn exerts a force on the bird in the upward direction, that is reaction force. Here is an experiment which proves Newton's third law of motion. Materials required: 2 spring balances of different least count, an iron stand fixed on a table. Procedure: arrange the stand. Take 1 spring balance. Note the least count of the spring balance. 5 divisions is equal to 0.25 n. That is, 1 division is equal to 0.25 divided by 5 is equal to 0.05 n. Fix 1 spring balance to the stand. Now, take the second spring balance and attach it to the end of the first spring balance. Pull the second spring balance away from the stand. As you pull the spring balance, you will feel that the spring balance is being pulled back. Both the spring balances will show the same force. Repeat the process. The two spring balances will continue to show the same forces. Tabulate all the readings. So we can conclude that when the second spring balance exerted a force on the first, which was the action force, the first spring balance also exerted an equal and opposite force on the second, which was the reaction force. Action and reaction forces are equal in magnitude but opposite in direction. Action and reaction forces act on two different bodies at the same time, so they do not cancel each other. Hence, Newton's third law of motion is verified.